What if life on Earth could have been built on something other than carbon? After all, silicon is right below carbon on the periodic table, so why didn't nature choose it? Have you ever wondered if aliens might look completely different from us? Not just more arms or funny-looking ears. What if they were made of something else entirely? What if, instead of being built from carbon like every living thing on Earth, they were made of silicon? It sounds like science fiction. A creature made of rock and crystal. But it's a real scientific question. Silicon sits right underneath carbon. They're in the same family, so they behave in similar ways. So, why did life on our planet choose carbon? This isn't a vanilla versus chocolate choice, it's chemistry and physics. Our first big reason is all about versatility. Think of carbon as the universe's ultimate Lego brick. A single carbon atom can link with others to form long, stable chains. These chains can branch, they can twist and turn. They can even loop back to form rings. This shape building lets carbon be the backbone of many molecules. Compare a complex branching carbon molecule with a more rigid silicon-oxygen chain. Long strands of DNA hold your genetic code. Complex folded proteins act as tiny machines in your cells. Carbon is social. It bonds with itself and many other elements. Silicon can form chains, but there's a catch. C-side bonds are weaker and break easily, especially around oxygen. Silicon prefers oxygen, building rigid silicate networks, rocks. Life needs flexible, stable variety, sugars, fats, structures like cellulose, and information molecules like DNA and RNA. Our second reason brings us to energy and temperature. Life operates in a Goldilocks zone, not too hot, not too cold. Bonds must be strong enough for stability, yet weak enough to break and reform with manageable energy. That's crucial for metabolism and building new cells. Carbon chemistry hits this sweet spot at Earth-like temperatures. Silicon loves oxygen, forming silicon dioxide. You know it as sand, quartz, and glass. SiO2 is a very sturdy solid. Those bonds are extremely strong. Great for rocks, terrible for biochemistry. Breaking SiO requires tremendous energy, far more than a living cell can typically muster. Once silicon locks into rock, dynamic lifelike chemistry grinds to a halt. Enzymes manage carbon reactions because carbon bonds are tunable, reliable yet manipulable when needed. SiO networks are too stubborn for the gentle, precise chemistry life depends on. It's like building a delicate watch with superglue instead of tiny screws. On Earth, where water is liquid, silicon wants to be a rock. Maybe on much hotter worlds, silicon chemistry could stay fluid and reactive. But here, carbon is simply better suited for the gentle dance of life. Let's dig deeper into oxygen, one of the most important clues in our mystery. Every time you breathe out, you release carbon dioxide, CO2, a waste of metabolism. At Earth's surface conditions, CO2 is a gas. It dissolves in water, rides your blood to your lungs, and you exhale it. An elegant, efficient disposal system that keeps energy flowing. Now imagine silicon-based life. Its equivalent waste would be silicon dioxide, CO2. SiO2 isn't a gas. It's a solid, sand, quartz, a mineral. Can you imagine trying to breathe out grains of sand? A biological nightmare. It couldn't exhale it. It would need to excrete solids, slow and complicated. CO2's gaseous state is vital for planet-wide cycling. Plants, algae, and some bacteria take in CO2 and, with sunlight, turn it into energy-rich molecules via photosynthesis. That's the carbon cycle, a beautiful, sustainable loop. SiO2 doesn't float in air, it settles and becomes geology. Recycling it needs erosion or volcanism on million-year timescales, not life's fast tempo. CO2 as a gas and SiO2 as a solid, that single difference makes carbon the practical choice for a breathing biosphere. Our third truth takes us into the vastness of space. Carbon and silicon are forged in stars through nuclear fusion. Carbon is the fourth most abundant element after hydrogen, helium, and oxygen. When stars die, they scatter carbon across the cosmos. Gas and dust clouds collapse into new stars and planets, seeded with these elements. We've detected over 100 carbon-based molecules in space. Alcohols, sugars, even amino acid precursors. Carbon chemistry starts early, long before planets exist. Silicon, meanwhile, tends to form silicate dust and rock-forming minerals. Early Earth was bombarded by comets and meteorites, rich in water and pre-made organic molecules. It's like baking. The carbon recipe arrived pre-measured. The silicon recipe required grinding up rocks to get started. Nature follows the path of least resistance. Evolution needs novelty and memory, change without collapse. DNA, a carbon molecule, stores information for generations, yet unzips and copies with ease. Small mutations create variation for natural selection to test. Carbon's versatility lets tiny tweaks create new molecular functions. Silicon's strong ties to oxygen resist subtle change, more like sculpting concrete than bending wire. For the long, winding road of evolution, carbon is simply the better vehicle. Cosmic abundance plus chemical adaptability gave carbon a massive evolutionary edge. First, unmatched chemical versatility. Second, perfect performance in Earth's temperature range with a gaseous oxide. Third, cosmic abundance and a head start for life. Does this close the door on silicon life? Maybe not. In extreme worlds, silicon might compete. If life evolved differently on another planet, could silicon life actually exist somewhere out there? If you love questions that make you rethink science, don't forget to like and subscribe to Physics AI.